All right, today we're going to tell a story. It's the story of a C++ object, and we're going to follow its entire life, from just an idea to a real living part of your program, and then, finally, to its graceful exit. So let's trace this journey, from blueprint all the way to dust.
I mean, seriously, think about it for a second. The software we use every day is unbelievably complex. So how on earth do programmers manage all that? How do they stop these massive systems from just collapsing into a tangled, buggy nightmare?
Well, the secret, at least in C++, is that you have to start with a really good plan, a blueprint. This is the whole idea behind object-oriented programming, and it's what lets us build code that's not just powerful, but also organized and, super importantly, reusable.
So, what exactly is this blueprint? Well, in C++, we call it a class. This is our starting point. It's the absolute heart of how every single C++ object is created. A class is basically a template, and it defines two really important things. First, you've got the data it holds. We call those its attributes. Things like its color or its size. And second, you have the functions that can work with that data. Those are its methods, which are basically the actions the object can perform. And here we can see that idea in action. This makes it way more concrete. We have a class here called suryansh. The integers a and b, those are its attributes. That's the data it holds. And message is a method. It's something an object built from this blueprint can actually do. See how it bundles the state and the behavior all into one neat package?
Okay, so we've got our blueprint. But a good blueprint also has to have some safeguards built in. You wouldn't want just anyone coming along and messing with the foundation of your building, right? Well, it's the exact same idea with our code. The solution to this is a really powerful but actually pretty simple idea called data hiding. We basically make the core data private, so it's only accessible by the object itself. This protects it from being changed accidentally from the outside, which is absolutely crucial for keeping your program stable and reliable. So the key takeaway here is that data hiding isn't about being secretive just for the sake of it. It's a security measure. By hiding an object's internal workings, we guarantee that its data can only be changed in very controlled, predictable ways through its own methods. And let me tell you, that drastically cuts down on bugs. Let's look at the code to see how it works. See that little private keyword? That's the magic right there. It acts like a wall around that integer var. Now, the functions takeInput and display, which are part of the class, they can get to it no problem. But any code outside of class A, it can't even see that var exists. Access totally denied.
Now, people get data hiding and encapsulation mixed up all the time. So let's clear this up once and for all. This table nails it. Encapsulation is the act of bundling everything together into that class. Data hiding is the technique of restricting access to the data inside, usually with that private keyword. So think of it this way. Encapsulation builds the box, and data hiding puts a lock on it.
All right, we have a secure blueprint. Now it's time for the really cool part, the magic moment where we actually bring an object to life. So how does a blueprint become a real living object in our program?
That is the job of a very special function called the constructor. Its name is always the same as the class name, and it has one supercritical purpose: to initialize a new object the very moment it's created. This makes sure it starts its life in a valid, predictable state.
And what's great is that we have a few different options for how we bring these objects into the world. C++ gives us three main types of constructors, and each one serves a slightly different purpose for getting our objects set up.
The default constructor is kinda your basic, no-frills option. If you want more control, the parameterized constructor lets you pass in initial values right away. And if you need to create a perfect clone of an object that already exists, you'll use the copy constructor.
Now this is what's so fascinating. You never actually call a constructor like a normal function. Look at the main function here. That single line, a_1, that's all it takes. The instant that line runs, the constructor a_aka is called automatically. This is proof that it's a special lifecycle event, not just some regular method you call yourself. So, our object has been born. It's been constructed, it's been initialized. Now let's talk about its life inside the program and, just as important, what happens when its job is finished.
During its life, an object often needs to refer to itself. That's where the this pointer comes in. It's this implicit pointer that's just available inside every method, and it always points back to the current object. It's basically how an object says, hey, I'm talking about my own data right now.
And of course, what goes up must come down. The opposite of the constructor is the destructor. You can always spot it because it has that little tilde symbol in front of it. Its whole job is to do cleanup just before the object is removed from memory. Releasing things like files or network connections it might have been using.
This slide right here shows the entire story in one beautiful shot. When demo obj runs, boom, the constructor is called. Then the line inside main function gets printed. And finally, when the main function ends and obj goes out of scope, the destructor is called. Again, automatically. It's this perfect, symmetrical life cycle. Setup and cleanup, all handled for you. Before we wrap this up, there are a couple of other really powerful tools I want to mention. These don't belong to any single object, but to the blueprint, the class itself. We call these static members. A static variable is kind of like a shared scoreboard for all objects of a certain class. It doesn't matter if you create one object or 1,000 of them, there's only one copy of that static variable, and they all share it. It belongs to the class as a whole, not to any of the individual objects.
But what happens if an object needs to live on even after the function that created it is finished? For that, we use the new keyword. It allocates memory on what's called the heap and, you guessed it, calls the constructor. But this comes with a huge responsibility. You have to remember to use delete later to free up that memory. Delete calls the destructor and prevents nasty memory leaks. They are a matched pair. You should never, ever use one without the other. So there you have it, the entire journey. A class acts as the blueprint, a constructor brings an object to life, and a destructor cleans everything up when it's all done. This whole life cycle is what allows us to build complex, reliable software. So, the only question left is, what amazing things are you going to build with it?